What if you could just look at a crazy long math equation and know exactly what its graph is going to do? Well, you can. In this explainer, we're going to unlock a really cool algebra secret that lets you do just that. Okay, check out this beast of a polynomial. It looks pretty messy, right? Lots of terms, big exponents. But I promise, by the time we're done here, you'll be able to tell me what the ends of this graph are doing. Are they pointing up or down in literally 3 seconds? No joke. So let's dive in. So, how do we tackle these monster functions? Well, the secret isn't some brand new, super complicated formula. Nope, it's actually hidden inside a simple shape, something you've probably known about for years. You remember the parabola, right? Good old y equals x squared. When it's positive, you get that classic happy face shape, where both ends shoot up towards the sky. And if you stick a negative in front of that x squared, it flips over into a sad face, and both ends point down. This super simple up-up or down-down thing, that's our key. That's the whole secret. Okay, now we're gonna take that basic idea and level it up. We can basically supercharge that parabola logic into a really powerful tool called the even degree rule. And this thing works for all kinds of bigger, crazier polynomials. So here it is, the rule itself. It's actually really straightforward. If the biggest exponent in your polynomial, that's what we call its degree, is an even number, like 2, 4, 6, 8, then the ends of the graph have to point in the same direction. It's a must. Either they both go up or they both go down. That's it. Okay, but why? Why does this rule even exist? What's actually happening with the numbers that forces the left side of the graph to play copycat with the right side? It all comes down to one simple fact. Even powers totally eat negative signs. Just think about it for a sec. If you take a huge negative number, let's say negative 1,000, and you square it, what happens? It becomes a massive positive 1 million. The negative sign just vanishes. And the same thing happens if you raise it to the fourth power or the sixth or any even power. That even exponent is like a negativity destroyer, guaranteeing that both far ends of the graph behave the same way. So what does this all mean? It means there are only two possibilities for any of these even degree polynomials. If the number in front of that biggest term is positive, both ends go up up just like our happy face parabola. And if that number is negative, well, both ends go down, down/down, sad face. See? It's just the parabola rule on steroids. Okay, enough with the theory. Theory's great, but let's see this thing in action. We're going to put this rule to the test with 3 different examples, and we'll start easy and then get a little trickier. All right, here's our first one, a nice, straightforward polynomial. The goal here is simple. Figure out its end behavior without even touching a graphing calculator. Okay, let's break it down. Step 1, find the highest degree. That's the x to the 4th power. So the degree is 4, which is an even number. Step 2, what's the sign of the number in front of it? It's -3. So we have an even degree and a negative leading coefficient. And what does that mean? The ends go down/down. Boom. Done. Okay, example number 2. Now this one has a very common trap baked into it. See how the terms are all jumbled up? They're not in the usual order. This is designed to trip you up, but we're not gonna fall for it. This is exactly why you have to scan the entire function first. Don't just look at the first term. The most powerful term here is actually the x to the 8th hiding at the end. So our degree is 8, that's even. And the number in front of it? Well, there's nothing there, which just means it's a +1. So we have an even degree and a positive leader. You know the drill. The ends go up/up. All right, for our last example, we've got something in factored form. Now, this can look a little scary at first, but trust me, the exact same rules apply. We just need to do a tiny bit of detective work before we can get our answer. First, we need the total degree. To get that, we just add up all the exponents on the x's. So we've got an x squared, that's a 2, then an x in the first parentheses, that's a 1, and another x in the second parentheses, that's another 1. So 2 + 1 + 1 gives us a total degree of 4. And hey, 4 is an even number. Now for the sign. We just multiply the numbers out front. We have a -2 times the +1 in front of the first x times the +1 in front of the second x. That gives us -2. So we've got an even degree and a negative leader. The conclusion? The ends go down/down. Okay, you've seen how this works. It's pretty powerful, right? Now to really make sure this sticks, let's quickly go over the most common traps people fall into. This is all about focus. You have to train your brain to tune out the noise. You need to ignore the order of the terms, and you absolutely need to ignore that lonely constant number at the end. Your one and only mission is to find the single term with the biggest exponent. That term, and only that term, tells you everything you need to know. So let's lock it in. The two big pitfalls. Number 1, never assume the first term is the boss. And number 2, that constant term at the end, it's useless for end behavior. Completely ignore it. So you might be thinking, okay, cool trick for my math test, but when am I ever going to use this? Well, you'd be surprised. This concept is actually huge in the real world, especially for people who build things, like engineers. Think about a huge suspension bridge. The massive cables that hold it up form a shape that's modeled by, you guessed it, an even degree polynomial. Engineers absolutely rely on knowing that the ends inevitably go up. That's not a guess, it's a mathematical certainty. And because they know the ends will always pull upwards, it tells them exactly how they need to anchor the whole thing deep into the ground. So, you see, this stuff isn't just abstract math for a textbook. Understanding how these functions behave has real, tangible consequences. It's a piece of the puzzle that helps make sure the bridges we drive over every day are safe and stable. It's pretty important stuff. So, there you have it. We've totally cracked the code for even degree polynomials. Their ends will always go in the same direction. Which leaves us with one last big question to chew on. Now that you know the secret of the evens, what do you think the odd degrees do?